The FRQs. The good news is they're predictable. At least the format of them are. The situations, you're on your own. Could be anything. Could be wild. But it's okay. It's always super simple. So find a situation that we have observed and worked with in class already that is very similar, and you'll be good. All right, so we got 4 FRQ questions, 100 minutes, 40 total points, exactly half of the exam. Question 1 will always be mathematical routines across all your AP Physics exams. Question 2 will always be translation between representations. Question 3, experimental design. And question 4, qualitative, quantitative translation. I'm in the way here, so you can't see those points. So question 1 is 10 points, question 2 is 12, question 3 is 10, and question 4 is 8. All right, let's look at question 1. Here are my patterns that I have observed and how these points are typically broken down. There's going to be some variances, but I'm feeling pretty confident about a lot of this. Question 2 has some wiggle room, but question 1, the points for part A, where there are 7 points, are always the same kind of 7 points. This order, I've seen it kind of mixed up where points 1, 2, and 3 are matching up with this as the first 3 points, or maybe they're put down there as points 4, 5, and 6. So there's just some changes that might happen, but in general, part A, 7-pointer, a lot of derivations. Let's do it. So a lot of times you'll get 1 point, the first point, for a correct selection or drawing and an attempt at a relevant justification. Attempt, not a correct justification, but an attempt. So don't just check a box, don't just draw a little graph. Attempt to explain what's going on to get that point. Even if you're not really sure what the heck is even happening. Okay. We're hoping you get it right. We're hoping you can predict what the correct answer is. But for your justification, a quick attempt. Point 2, we're using physics facts or principles in our justification. This point can be earned even with wrong answers, as long as we're not using bad physics. Bad physics is saying the heavier object will fall faster than the lighter object in the gravitational field because it has more mass. We know that's not true. That can't be correct, so that means you're not going to get that point. Point 3, a multi-step derivation using the correct formula from the equation sheet. We use 1 or 2 formulas, maybe 3 formulas from the equation sheet, and see how they're together to derive. Derive means to show all of your mathematical steps. Multi-step means don't just write the equation. You're going to have to do a little bit of algebra here to solve for what the question's asking you for. Point 4, a lot of times this is an algebra or calculus step, so making sure you're doing something algebraically correct or setting the correct bounds on your integral, whatever the case is for your derivation. Point 5, usually that's a correct answer with correct variables. Point 6 is going to be a second derivation, and it's going to be related to the first situation. But you're going to need to use information from your first derivation and probably plugging it into your second derivation. So if you solve for a equals 2x plus 7g for your first derivation, you're going to use that 2x plus 7g as your acceleration in your second derivation. If you got the first derivation completely wrong, you have no clue, you don't know anything, we're going to still write something down for that first derivation as our answer, so we can use it for the second derivation, so we can perhaps get these 2 points. If we're using a wrong answer, we're going to get a wrong answer, but that doesn't mean we're going to be penalized twice for it. So the last point you get for having the correct answer with correct variables. So if you have the wrong answer because you used the wrong equation, you're not going to get that last point. But you could still get maybe that 6th point. Maybe you only got 3 or 4 of these points. It's okay. That's okay. We're aiming for anything over half. Anything over half, and we're happy. Error carry forward. What that means is if you make that error in part A, you're penalized for it in part A. You're not going to be penalized for it again in part B. So keep going. Go with it. If part A was a numerical answer, then we're going to use that numerical answer that we knew was wrong for the second derivation. Part B, we'll be given a new situation. So we're going to do another multi-step derivation, use our correct equations. We're going to connect an equation to a situation. So if density stays constant and radius increases, what happens to mass? Those types of things. So we're going to change something and see how it is affected. And then finally, the last point for question number 1 is having the correct answer with the correct variable. This is the tricky one. This is tough, especially if derivations or deriving are your weak point. If that's true, then you need to really focus on the weak point. So do a bunch of derivations. In OneNote, there is a study guide that has important derivations in there that will walk you through step by step how to do these derivations. Do them together so you can check yourselves. To derive, you're going to start with 1 or 2 relevant equations from the equation sheet. If you have them memorized, this makes the whole process a lot easier. If you don't have them memorized, a good way to memorize them is to write down an equation, maybe v equals v naught plus at, and then say, oh, there's an a there. Let me find another equation that has a in it. A equals f net over m. Okay, that's Newton's second law. F. There's an F frictional force. Frictional force equals mu times Fn. And what I'm doing is I'm just picking a variable and then writing down that equation on the next line as I memorize what these equations are called. This is going to help you see connections between these relationships. So that way these derivations will go a little bit quicker, a little bit smoother. It's never too late for this. Make reasonable assumptions that we've been making all year. If it doesn't mention air resistance, we're not going to bring in air resistance. If it doesn't mention a string has mass, then we're going to assume it's an ideal string. Massless pulley is a reasonable assumption, unless it says pulley has mass m. That means it has a rotational inertia. If there's a constant torque, that means there's a constant angular velocity. Then you're going to substitute. Does your equation have only the available variables? So when you have to derive an equation, it's going to say derive an equation for r in terms of mu k, m, and physical constants as necessary. So by giving you those constraints, the mu k and I forgot what the other variable is. M. By giving you those constraints, mu k and m, that's your hint. Find an equation or 2 equations that have mu k, m, and whatever you're looking for r. Physical constants just means little g or big G for AP Physics 1. There's some more for E&M, or mechanics, we're pretty much just going to have big G, little g. But for AP Physics 2, there's other ones as well. Like your mu naughts versus your mu's, like that. Mu k and mu s in AP Physics 1 and AP Physics C are not physical constants. Okay? So, does your equation have only the available variables? So we're not going to use an equation that has x in it because x isn't anywhere, unless we're calling xr. If not, we might need to use a second equation and then substitute. Think about these equations as relationships. Like impulse momentum relates force and velocity with time. Power relates force and velocity without time. Next, we're going to rearrange. We're going to use our algebra or calculus to isolate the target variable. your AP Physics C, look for the phrase write but do not solve a differential equation. In that case, we're going to substitute a differential term for the term that is changing. So if we have changing acceleration, that would be dv dt. If we have changing angular velocity, then maybe we're going to use d theta dt. Or if x is being used because of spring constant or something like that, let's use our second derivative for x, d2 e squared times x over dt squared. Second derivative. Finally, after you have solved your equation for the variable we're looking for, reread the problem and make sure we're only using the variables listed in the constraints. The very last step. Should ft actually be called capital T? Should weight force actually be called just capital W? Look for these small little things. Should x be called R or capital R? Make sure your units and variable names match exactly.